Thanks for the organization and for the invitation. I live quite close to IHP, not far from Paris, and I start to apologize not to be among you today and this week. But at the beginning of the week, everybody in my home has been tested positive for COVID-19. So in our patch, we are all infected now. And I think it's better to avoid to move to other patch and participate to the spreading of the epidemics. And so first, this picture is to apologize and not to be there. I would have been glad to and see people I've not seen from some time. And second, it's maybe a motivation for the problem I would like to discuss with you today, which is to study propagation of epidemics on population which are spatially structured by a large random metapopulation. The second reason to explain that is that my voice is a bit broken, so I hope you hear me correctly. Please stop me if there is anything which is ununderstandable. So as I told, the motivation is to study epidemics on large metapopulations, and this is a joint work with Michele Salvi, which is now in Roma, in Tor Vergata. The original motivation is not to study COVID-19 or epidemics for humans, but epidemics spreading among farms in the French networks of commercial exchanges in France. And this is part of INR project conducted by Elisabeth Avergu, where we study the propagation of some diseases and the diseases which are motivated this project are listed here. In particular, you probably have heard about the dramatic effects of foot and mouth disease. From these events, there is a complete tracing of animals, which gives a very good and very large data set to describe how commercial exchanges happen. And so for us, it was a source of data to model how animals are moving among this metapopulation of farms. The project regarding the mathematical modeling has been split in two parts. Essentially, one part was to try to understand locally things, so on a small network of farms, so on a small metapopulation. And the second part was to study globally what can happen and what is the speed at which the illness, the disease may propagate. And globally, what we see is a very large metapopulation, a very large number of vertices in the graph. The order of magnitude of the number of farms in France is 100,000. So this motivates to try to give a reduction of the model. The number of parameters behind the explicit graph is just amazing, and we would like to understand what kind of reduced approximation may be relevant with a limited number of parameters, and obtain from this reduction the key parameters to describe the evolution of populations. And the kind of motivations that you can imagine is to try to improve to the control of the propagation, and in particular, how to test the most efficiently the animals what kinds of measures can be relevant to limitate the propagations, and many things like that, which are common questions that we found actually in other problem of propagation of disease. And we had the same kind of question with the crisis with the COVID-19, and in particular trying to regulate the motion of individuals, both inside countries and between countries. This is the same kind of issue, and again, is a very large network, so a complex object that we try to simplify in some scalings. So, if I want to put this work in a maybe more general context, in particular because we had a nice talks yesterday about metapopulations, so spatially structured population where individuals live in patches and may move from patches to another. And here the motivation were different. It was for spatial ecology with other questions, but there are many common points with talks of yesterday, and in particular with the talks of Fridtjof Lüscher. I hope I spelled it correctly. I pronounce it correctly, because we will see some homogenization effect. The common point in particular with this framework is that the landscape corresponding to the spatial description of the population is very heterogeneous, and at some scale we hope some averaging, which in case of spatial structure is often a non-trivial averaging, and that will involve what I will introduce, which is a nice topic well developed in probability, which is a stochastic homogenization. So there is essentially two ingredients in what I'm talking about. A very large network, which is a randomization of some point process. I will explain it just after. And then population dynamics, if I forget the motion between patches, population dynamics will be only local. So birth, death, infection will only depend on what happened inside the patch. So it will be a size-dependent rate with a dependency which is only local. So this is for the general framework. And let us turn to the model we have considered. The model we have considered is I think we have tried to choose a model for which we can make some computations, and we have a nice probabilistic structure, and that's one reason to choose the Poisson point process to describe the set of points corresponding to locations of our metapopulation. So our patches are distributed following a Poisson point process. We have tried to make something which was coherent with data. So when you look at data, the location of farms do not look like homogeneous Poisson process, do not look like a typical realization of homogeneous Poisson point process. But adding some non-homogeneity in the intensity allows to get a good picture. I'm not speaking about the non-homogeneous case, but it's something that can be added in what I will present quite easily. And so that makes a framework which is, we hope, both mathematically tractable and relevant regarding our motivations. And the second feature is to describe how individuals go from one patch to another. And this will depend here only on the distance between two patches. So the closer the patches are, the more the individuals may move from one patch to another. So this is only depending in the distance between the patches, the rate of transition of individual from one patch to the other. In particular, it is giving to the process describing the motion, a very important property that we will exploit strongly. There is a reversibility. You have the same rate to go from x to y than to go to y to x. This assumption is important, and relaxing it is, I think, interesting, but probably a challenge. At some scales or another, I think we need some reversibility to, in particular, to ensure stability. And we are asking more than the fact that the rate of transition depends only on the distance between patches. The rate of transition depends on this distance and decrease fast with the distance. Let's say exponentially fast. So this is forcing, at a macroscopic level, individuals to move locally. We are not allowing in this. It's very rare to make a very large jump. Again, if you look at data, there is indeed a strong dependence with distance, but to get a more realistic model, that will be nice to have at some point a non-local term, and it's, I think, an interesting perspective. But that's not what I'm talking about today. Well, some extension of what I'm saying are quite direct. The important point is that, well, when you look at two boxes which are far, you get some independence between what happens in one box and one other box. This independence is for free in the Poisson structure. If you want to go to more complex graph, you need some independence asymptotically, where you take two parts of the graph which are very far. This goes with this local behavior I was mentioning. The kind of thing you can have, which is not a problem and which is relevant, looking at the data for exchanges on the French network, is to add a population on edges. Here, whatever the patches you consider, you have a positive rate of transition only depending on the distance. To be closer to what we see looking at exchanges, it will be interesting to add a percolation of edges, so to delete some edges with some probability, saying that two patches may not exchange even if they are not so far. This is not a problem to have in what I am talking. I repeat, the important points are the fact that there are some independence far, some local behavior, and some reversibility somewhere. So in particular, if you want to delete edges, I would prefer that you do it in the two directions simultaneously. Okay, so this is the model we are considering. I'm not giving details so far on the demographic or epidemiologic part. It's a classical birth and death rate, size dependent locally at the end, but for large part, it's the part we have just completed now. I am actually considering a fixed birth and death rate, and I will explain at the end the work in progress, how it extends to local competition or non-linear term, which are important when we look at propagation of epidemics, which are not in a very large patch, in a patch where the population is not large enough. So I will give detail when it is necessary. The kind of question we have considered are the following. First, to construct the process was not as easy as we expected when we want to construct a process which is defined on an infinite metapopulation. So if we want to consider a non-bounded set with a population which can be at initial time on every patch, so with a non-bounded initial population, the fact that the process is well defined is already a question, and I will explain a bit how it can be checked and what assumptions are required at this point. Then we have a population process on a very large network. And the question coming is, how could we reduce it? What kind of approximation we should expect looking at the macroscopic scale, the density of population. So I will consider a first regime that we have determined with Michele Salvi. And maybe at the end, I will explain a bit more complex multi-scale models that we are considering now and trying to go closer to our original motivation. Some important facts we are using. I have told that it is important to have some reversibility at the level of movement, and indeed we are using strongly results and techniques coming from particle system and hydrodynamic fluids in random media, and in particular in stochastic homogenization. So I will mention the results when I will use it, but I give here important names that we have followed for this work. Another important point is that we are considering a quench result. So that means that the result will hold almost surely regarding the realization of the metapopulation. So, in particular, when considering macroscopic approximation, we will get some partial differential equation at the end, reaction diffusion PDE to describe the population at the macroscopic level. And the parameters of this PDE are not depending on the realization of the random metapopulation. So this will be quench result with constant parameters regarding the underlying spatial structure. Okay, to maybe give an idea of why we have some troubles, but interesting troubles, to go from what is known in a particle system and stochastic homogenization to our framework. I think the main reason is that looking at the movement, there is some reversibility property of the process, but adding, for instance, just a birth or death is making us lose this reversibility property. And this is something I will show a bit later, how we can exploit what is reversible at the level of moment and combine it with population dynamics. So let us define the process. This is quite direct to define the process if you restrict the metapopulation to a finite box. So you forget all connection which go outside this finite box. Then you have no problem to define the process. No accumulation of events is possible. You just follow event after event the evolution of your population, and you have a finite structure for which all computations can be done, but where you still can exploit the reversibility, since the restriction of the graph to a finite box is again reversible structure. So you make all computation on a finite box, and then you have two extensions that you hope are possible. First, consider an initial population which live in a finite box, but let this population evolve inside an infinite metapopulation, so on the whole plane. So now your individual start from this bounded box, but can go outside and maybe go quite far. The only thing you have to check to be sure that you can define correctly the process is that you have no acceleration of motion, which may be possible because the rate of transition, the connectivity of the nodes in the graph are non-bounded. What I call connectivity is simply that at a point x, the total rate of transition is the sum over all patches of the rate of transition to go from x to y. In this setting, when you consider the full plane, you may have points which have a very large number of neighbors, which makes this rate of transition non-bounded. But Poisson point processes are quite nice. They do not have heavy tails. Their tail is small enough so that you can control, when you make the box larger and larger, the connectivity of nodes. And this is not increasing fast enough to provoke any kind of accumulation of events which will provoke explosion and prevent you from defining the process. So now you have defined your population model, starting from a finite box and allowing population to live in infinite metapopulation. And now what we want to do is, by a monotone procedure, to allow to start with individual living on every patches. And here you need to check that you have no explosion locally. When you start with an infinite population, instantaneously you will have an infinite number of events, transitions or births or deaths and so on. If you want to define your process, or at least the way I know, is to consider locally what happens and define your process locally. And to be sure that you can define it in a local way, without explosion, you need to check that you have you control the number of individuals which may arrive in a finite box during a finite time. As you have infinite number of individuals, it may happen that an infinite number of them arrive in your box in a finite time. Well, this is something we can control, which is something which is classical questions in particle system and branching processes. And well, I mentioned branching processes because there is a natural way to control it is to use the first moment estimate. So to compute the expectation of the number of individuals in a given box, and to compute expectation of number of individuals we enjoy when we have a linear structure. And this is possible to dominate the original process by a linear structure, so a branching process, simply by forgetting death, forgetting the disease, forget the dependency of the birth rate regarding the local density. So the only assumption that you need is that you have some bounded individual birth rate. And then you get a process where individuals move and reproduce independently. For this, you have first moment computations which can be done by using the linear operator. And this is enough to dominate the problem with local interactions and death, simply because when you have one individual, this individual may move a lot, is born at most once. Once you control it, well, he can die only once, and he can just be infected once and recover once. So if you control motion and birth, that's only a problem of a factor 3 or 4 to control the total number of events, and so to check that everything is well defined and characterize the martingale problem associated with this process. So it's what we do, and we are inspired by techniques where we want to register all events. So we had to control the motions. If we want to check that we have no accumulation of events, we in particular want to check that we have no accumulation of motions in a finite time. So we cannot just control the number of individuals alive at time t. If I know how many people we are at time t, I have no a priori bound on the number of motions these individuals have made during their life. Maybe some of them have moved a lot. So to do that, but keep the linear structure, the branching property at the level of the process, what we do is, I think, something quite classical, is to register events simply by saying that when one individual goes from one patch to another, this is a real individual, a live individual. He leaves a ghost. So each time somebody is moving, he leaves on the patch he left a ghost. The ghost is no longer moving or giving birth or dying. It's just to keep track of the motion from one patch to another. The good point is that you still have a branching property here, and you still have a first moment, which is a linear operator. And the fact that there is a reversibility for the movement makes that there is a natural left eigenvector for this operator, which allows for a rather nice computations. And this control is important for the construction and not only. So we have constructed a process which lives on an infinite metapopulation with motion, birth, death, infection. But now I'm just considering what happened with birth, and I will say at the end what happens, or what is expected for the part which is still in progress. What happens when we have the more demographical or epidemiological components. So we have a Markov process on the metapopulation with a generator and an associated martingale problem, which correspond to square integrable martingale, for which we have a quadratic variation with the usual form. I won't use this so much, and as time is going, I will go to the second part. If there are no questions for now about the model. So now we have this population model on an infinite network, and we are trying to find some relevant macroscopic approximations. So we have in mind to scale time and space and natural scaling, even if it's not a centered motion locally, because depending on where the points are, you may go more on the right than on the left. The isotropy in law that you have at the level of the Poisson point process makes that you expect some compensations and some diffusive scaling, and this is indeed what can be seen. And diffusive scaling will consist in looking at the distance we had and renormalize the position of points by 1/n. So we are compressing distance, and we are accelerating time to see a movement, diffusive movement at the microscopic scale. We have two scales, which at least actually we have more than that. But two scales were interesting for us in the first part of this project. It's the link to the question on how you relate the scale of motion to the scale considering demography or epidemics. in any case, and I will explain a bit this more, you are interested in terms of motion by a time scale where you accelerate time with factor n square, which is the usual diffusive scaling. So you have lots of motions, which are represented here by this small jump along the time. You have lots of motions before this time n square time t. And then you had some demographic or epidemiological events, and at least two scales were natural in our case. And we have started by the simplest one, and we are considering the maybe more difficult one now, which actually they are not so far. And the first, the simple case allows to understand actually a large part of what happened for mathematical arguments, at least for us, in the second scale. So two scales are natural. The first is simplest. The other is more relevant regarding our motivation for epidemics among farms, and that's one of the reasons to consider now this scaling. So the case I'm considering here is a case where the demography is slower than the motion. So during this time n square t, you have a lot of motions among patches, but you have not an explosion of the number of demographic or epidemiological events. So this corresponds to epidemics where people move a lot, or if you look at the problem of metapopulation mixing demography and motion, regarding your lifetime, you will go inside several patches, many patches. The other scaling, which is interesting and connected actually to the previous one, at least for the estimation I will show, is to actually consider common scales. So you have many epidemiological or demographic events during this n square time t scale. So I am considering this case now with the separation of scales, and maybe if I have time at the end, this links to work in progress. I may come back on this later. There is a common feature which I will show now about the way spreading occurs in space, but there are here in the case without separation of scales additional renormalization, because the populations are growing faster here, and we need some local renormalization to get again deterministic limiting object. Well, the key ingredient in both cases is that if you look at the motion of individuals, you indeed get something diffusive. And this is something we take from the literature. And there are a lot of works which I have discovered recently, which are very nice mathematics, and we are using them to deal with this issue. We are, in some sense, adding the demography on all that, and I will explain where maybe it's non-completely direct. What is quite remarkable is that, at least for me, is that when looking at this motion among the random metapopulation, we get some diffusion, so some Brownian motion when you flow one particle, with a speed sigma which does not depend on the realization of the Poisson point process. There is some law of large numbers coming from the fact that we compress space, and Poisson process, there is lots of independence between disjoint boxes. So we may expect some averaging, and indeed the speed is not depending from the realization of the Poisson point process, and in this scaling. And what is also quite remarkable is that the speed is mysterious. Well, I'm not able. You have to follow the works I mentioned below to explain why we cannot compute it, but why variational formula is giving some expression. Up to my knowledge, in one dimension for some periodic environments and so on, the speed coming in homogenization is explicitly computable. But in 2 dimensions and for these kinds of models, I don't know any explicit expression of the speed. But the fact, and there is a good reason for that, that it is a solution to some variational problem. And so the good news is that we have a speed which does not depend on the metapopulation realization, which is important for our purpose in applications, because it means that there is some robustness in the way we can reduce the problem of metapopulation to reaction diffusion, because we have some realization. We have a metapopulation which which is close to a Poisson point process, and we are saying that whatever the realization here, the speed coming at the macroscopic level is the same, and so this is interesting in terms of applications. I think. Well, maybe bad news is that it's not explicit, and we will have to go to numerical works both to see what can be said about the speed, and to check that it is relevant in our context regarding more individual-based models. Well, the question which may arise when you see such a formula and you look at your stochastic individual-based model is where this speed will come from when looking at my generator and trying some limiting procedure. And this is a nice theory that we exploit, and we use in particular here results of the people I have mentioned here, and for this part where we have some direct input from homogenization theory, this is due to recent works of Alessandra Faragionato that we used in our context. When you look at the motion of individuals, if you were in a context of regular space, so imagine that you have a lattice in 1 dimension. Patches are given by x plus 1, x minus 1. Imagine also, to simplify, that you can just move to the closest neighbor with equal probability. Then making a Taylor expansion of that is direct. Simply because you are looking at this. So you have one neighbor and the other. You make a Taylor expansion. The first derivative is cancelling because you have a plus and a minus. And the second derivative will appear. And the speed you will get is simply given by the rate at which you move. So you directly have a cancellation of the first order term, and you get your Laplace operator with an explicit speed directly given by the rate. Here it does not happen like that. When you are in a random world, well, I say what I understand of the problem. It's my way to understand it. I'm not an expert of that. So feel free to make comments if you want. So when you are in a random world, well, you do not live any longer on the lattice. So the closest neighbor won't be at the same distance. Maybe someone is closer than the other. So your rate to go to the right is greater than to go to the left in our model. When you do that, locally, you do not have a centered motion. You have a tendency to go here to the left. So the fact that the first order term is compensating is not direct, and this is due to the fact that when you accelerate time, you will see many patches, and sometimes tendency will be on the right, sometimes on the left. By symmetry of one-dimensional Poisson point process, you expect a compensation, symmetry in low, and that the first order term is disappearing and leaving a second order term. But as you see, this compensation is non-trivial. The second order term, its form is non-trivial either. And so making Taylor expansion is not the solution. At least I've not seen how to make it. And when following the works which are down in this topic, there are essentially two ways to if I understand correctly, to consider this problem. Either to look at the Poisson equation, which we did, and which we can use efficiently in our case, or to consider a compensation, a corrector of the motion. And well, the idea of the Poisson equation is quite natural. I say it informally. Our problem is to approximate the generator evaluated for function j, and we hope that it is close to a Laplacian operator with homogenized speed.
Excuse me, Vincent. I'm sorry to interrupt, but it's 6, so if you can try to conclude soon.
I'm concluding. I know I did not have time for everything. So I'm concluding. You replace this, but actually, okay. Thank you. So you replace this problem by considering the solution of this equation, and now your problem is bound to check that this function is close to this one. Okay, I cannot give the detail. But it's my fault. The difficulty we had when adding the population dynamics was that we are losing reversibility, and in particular, we are losing optimal inequalities we had in the context of just considering motion. So we needed to get maximal inequality for branching structure using at the level of motions, but plugging the motion inside the genealogy of the population. And there is a compatibility of the invariant measure with respect to population, which shows to you to go from one word to the other. Okay, this allows to get the convergence we expected. So in the simple case, that consists in saying that our stochastic process, if you look at the associated measure value, converges in low in the scoroscope space to a measure which corresponds to the solution of what we may expect, which is a reaction diffusion with homogenized coefficient. Okay, so I'm stopping here, and I'm not mentioning the extensions to more complex model that was the original motivation, but that's fine. Thank you for your attention, and sorry for the time.
Thank you very much for this very interesting talk. Maybe we have time for one question.
Hi, sorry. My question is, you said that individuals were doing like Brownian motions. I don't know if this corresponds to your biological motivation. Is it realistic to imagine that sick individuals really move around a lot? And if we should not imagine a limit in which a sick individual moves maybe once or twice before being detected and eliminated or something, I don't know.
You are right. That's the first modeling, but we hope that it's not so far the case you say, and that's a link with the two scales I mentioned. Cos are not moving a lot, but and that's the case we are considering now. And in particular, mat cos may move less and be detected and put outside the process. Well, I think we may discuss more later on that. Just one thing to say, that the two problems are not disconnected. That's what we are doing now, is that even if your cause moves just a bit and is infected at some time and then go outside. The problem when you look at the spreading of epidemics is that during the time it was infected, it will have contaminated somebody, which is moving again. And this is creating the homogenized spreading that we are speaking, and we think it's what we are doing, that you recover at these scales where, as you said, you have not so much motion for infected individuals. We are still recovering for spreading in other scales, not all, but in the one we are considering, we think that we recover again a speed quantified by this kind of homogenized coefficient.